Today, we're looking at a new paper called ToolOrchestra, Elevating Intelligence via Efficient Model and Tool Orchestration. It's from NVIDIA and the University of Hong Kong. And it really changes the game for how we should think about building high-stakes agentic AI systems.
It really does. I think the core breakthrough here is this realization that, intelligence doesn't just come from a massive monolithic model.
Right.
It can actually emerge from a really well-managed, coordinated system. It's all about delegation, not just raw scale.
And the results are they're stunning. The model they created, Orchestrator 8B, is an 8 billion parameter model, and it actually outperforms frontier models like GPT-5 on some of the hardest benchmarks out there.
Yeah, that HLE benchmark, humanity's last exam.
Exactly. On HLE, Orchestrator 8B scored 37.1%, which is actually higher than GPT-5's 35.1%.
And for anyone who actually has to deploy these systems, in the real world, the efficiency numbers are maybe even more important.
Oh, absolutely.
Orchestrator 8B is 2.5 times more cost efficient than GPT-5 on that same benchmark. And on others, it's beating GPT-5 while using, only about 30% of the cost?
And that efficiency isn't an accident, right?
Yeah.
It's literally baked into the training.
Yes.
The whole thing is trained using reinforcement learning, RL, with this really unique multi-objective reward function.
Exactly.
It forces the model to juggle three things at once.
Yeah.
Getting the right answer, being efficient with resources, and actually aligning with what the user wants.
So the bottom line is that this just demonstrates a powerful new way forward. You take a bunch of diverse, specialized tools and you manage them with a lightweight, smart orchestrator. It's proving to be more efficient and more effective for building these big, scalable reasoning systems.
Okay, so let's unpack that a bit. This orchestration paradigm. We all know that the big language models are incredible generalists.
Sure.
But when you try to solve really complex, deep problems, the HLE benchmark is basically PhD-level questions. Just using one model it's tough, and it's incredibly expensive.
That's the wall they're hitting. The standard approach is you take a powerful LLM, you give it a search engine, maybe a calculator, basic stuff.
Right.
But the motivation here was to mimic how humans solve hard problems. We don't just use a simple calculator. We call on external experts, or we use specialized software, things that have, greater than human intelligence in a specific domain.
So the orchestration paradigm is basically that in practice. You have a relatively small orchestrator model.
The brain or the manager.
Yeah. The brain. It takes the big problem, breaks it into smaller pieces, and then it delegates those pieces to the best specialized tool for the job. And those tools can be anything from a simple function to another, massive LLM.
But before they could even build it, they had to answer a really critical question. Why can't we just, prompt a huge model like GPT-5 to do the orchestrating for us?
And their pilot study showed that it just doesn't work.
It fails, yeah. It fails pretty dramatically because it brings in these really predictable systemic biases.
This part is so interesting to me. You'd think the biggest, smartest model would be the best manager, right? But they found two huge biases. First, this self-enhancement bias. When they asked GPT-5 to pick the best tool, it called on itself or its smaller version, GPT-5 Mini, something like 98% of the time.
It's like a CEO who just insists his own son is the best guy for every single job.
Right.
Even when a specialized contractor is way cheaper and faster, it just defaults to what it knows and trusts, which is itself.
And then you have the complete opposite, the other enhancement bias, which they found in smaller models. So, for example, Qwen 3.8b, it just defaulted to the strongest tool available, GPT-5, over 70% of the time.
That model is basically saying, look, I don't trust myself, so I'm just going to pass this off to the most expensive consultant we have on retainer.
Exactly.
And that completely undermines the entire goal of being efficient and, saving costs.
So if the model you're trying to use as a manager is just inherently biased about which tools it calls, well, you can't rely on simple prompting. It proves that managing all these trade-offs, cost, performance, strategy, it's just too complex. Instruction tuning isn't enough.
It confirms that, It confirms that this kind of complex tool orchestration really warrants its own dedicated training approach. One that's specifically designed to handle these nuanced situations where a model has to strategically call tools that are sometimes better than itself and sometimes worse.
Okay, so let's get into that dedicated training. How do they actually teach an 8 billion parameter model to be such a strategic, unbiased manager? The secret sauce seems to be in this ToolOrchestra methodology.
It is. They framed the whole thing as a Markov decision process, an MDP.
Right.
And for anyone less familiar, you can just think of the MDP as the structure of the decision-making problem. The state is the current context, the action is calling a specific tool, and the goal is to get the right answer while minimizing cost and latency.
And the whole process is iterative. It's this multi-turn rollout that can go up to, what, 50 times?
Yeah, up to 50 times. The orchestrator just cycles through, thinking with a chain of thought, making a tool call, getting the response, and then using that for the next step.
And the tools it's managing are incredibly varied. They built this unified tool calling interface.
And this is key. They didn't just give it a calculator. The tool set had everything from simple things like Tavily Search and a Python sandbox to really specialized LLMs, like a math-focused model.
Yeah.
All the way up to the heavy hitters like GPT-5 and Claude Opus 4.1.
And that variety of tools is so important because that's what creates the complex trade-offs, right?
Exactly.
Why call the cheap, fast math model for a problem if the huge generalist model is maybe slightly more accurate?
Mm-hmm.
The orchestrator has to make that call on the fly.
And that brings us to the real technical core of the paper, which is their novel multi-objective reward design. The final reward signal, it isn't just a simple pass or fail. It's this delicate balance of 3 different objectives.
Okay, let's start with the one we'd expect, the outcome reward.
Right. That's the simple one. It's a binary 0 or 1. Did you solve the problem correctly? Usually judged by a powerful external model like GPT-5.
Then we get to the really clever part, the efficiency rewards. This is what forces the model to be, cost aware. It gets explicitly penalized for using resources.
Yeah. A penalty for monetary costs and a penalty for wall clock time, so latency.
And they had to build a whole accounting system for that.
They did. They had to unify the cost. So they converted tokens from open source models, which, might be running on your own server, and tokens from proprietary APIs like GPT-5 into a single monetary standard based on what third-party APIs charge.
That's brilliant.
It gives the orchestrator a real financial incentive. It learns to use the cheaper local tools when it can.
It basically teaches it how to budget. But there was a third factor too, right? The preference reward.
Yeah, and this is all about controllability. This reward aligns the system with specific user instructions that go beyond just solving the problem. So if a user says they prefer, say, local search for privacy reasons, or they care more about speed than cost,
the model gets rewarded for following that instruction.
Exactly. It gets a higher reward if it adheres to that preference, even if it means being slightly less optimal on another axis.
So they used Qwen 3.8b as the base model, and for the actual RL training to juggle all these competing goals, they used an algorithm called Group Relative Policy Optimization, or GRPO.
Yes, and as you can imagine, RL training in an environment this complex can be really unstable. So they had to put in some pretty rigorous stabilization techniques, like filtering out bad trajectories to make sure the model was learning high-quality, reproducible strategies.
Okay, so a good RL agent needs a ton of high-quality training data, which for this kind of multi-step tool use is, well, it's pretty scarce.
It is, so they had to build their own. They called it ToolScale.
And how did they generate it?
It was this really creative 2-step process. First, they used LLMs to just simulate entire environments. They generated database schemas, thousands of entries, specialized tool APIs across 10 different domains: finance, medicine, travel, e-commerce.
Wow, so they built a whole little world for it to play in.
Pretty much. And then came the second step, task generation. LLMs would propose general intents, which were then turned into specific multi-step tasks. And crucially, they used a second LLM to make the tasks harder, adding constraints, making sure it required a very specific sequence of tool calls to solve.
And the validation for that data was incredibly strict.
Oh, absolutely. A task was only counted as a success if it met 3 criteria. Execution correctness, so the database had to end up in the right state. Process fidelity, meaning the reasoning process had to mention all the key info, and operation completeness. It had to touch all the right database entries.
So it's not just did you get the right answer, it's did you get the right answer in the right way for the right reasons.
Exactly. A traceable, correct path.
And that level of detail, it clearly paid off when you look at the performance metrics. They tested Orchestrator 8B on HLE frames and this thing called FethBench, and the results are they're consistently better across the board.
And let's just quickly define those. HLE is that complex PhD-level reasoning. Frames is all about factuality. And FethBench specifically measures function calling and its ability to use tools in a sequence.
The fact that this small orchestrator could lift the whole system to 37.1% on HLE, beating GPT-5, That's just a massive finding. It suggests that strategic management of resources can actually unlock a higher level of intelligence than a single bigger model can.
And you see that same trend everywhere. On frames, Orchestrator 8B got 76.3%, quite a bit higher than GPT-5's 74.0%. And on Hupbench, where it's all about scheduling, it hit 80.2%, easily beating GPT-5's score in just raw tool use.
Then you combine that performance with the cost analysis in the paper. I mean, the economic picture is just undeniable.
It really is. Orchestrator 8B just gets the best performance for any given budget. And it costs way, way less to get to the same performance level as the big monolithic models.
It's the perfect validation of that efficiency reward design.
It is. I mean, look at the alternative. They prompted a model like Claude Opus 4.1 to use some basic tools. Sure, its performance went up a bit.
But at what cost?
At a nearly 3 times cost penalty and 4 times the latency. Orchestrator 8B learned how to avoid that awful trade-off entirely.
So for anyone designing these systems, what does this actually mean? The key seems to be how Orchestrator 8B used its tools to avoid those biases we talked about at the start.
Exactly. When you look at the tool usage breakdown, the difference is just stark. The prompted models, they were terrible managers. Claude Opus 4.1 leaned way too heavily on GPT-5. GPT-5 just leaned on itself.
Right.
But Orchestrator 8B learned this balanced, cost-aware strategy. It only called the most expensive tool, GPT-5, about 1.6 times per task on average.
And Claude called it
6.2 times.
Wow.
Yeah. It showed real fiscal responsibility. It used the cheap tools when it could and only escalated the expense when it absolutely had to make sure it got the right answer.
And this strategic training also led to some really robust generalization. They tested it with tools it had literally never seen before during training.
Models like Claude Sonnet, Gemma, Coastral.
And even with a totally new toolkit, it still maintained its superior performance and its low cost. It somehow figured out the utility of these new tools just from reading their descriptions and then folded them into its budget-aware strategy.
It also showed it learned adaptive optimization, not just memorization. They threw completely different pricing schedules at it, from different API providers, and it adapted effectively. That confirms the training taught it the principle of cost management, not just one static optimal path.
And finally, that preference reward. It really proved its worth in the adherence test.
It did.
Orchestrator 8B was just remarkably better at following those tricky user preference instructions, like prioritizing low latency or using local search for privacy, compared to even really powerful systems like GPT-5. So it's not just smart and efficient, it's also controllable, which is huge.
Ultimately, yeah, ToolOrchestra proves that a small, strategically trained RL agent can be this incredibly efficient, controllable manager inside a bigger AI system, and it unlocks a level of intelligence and scalability that you just couldn't get by, piling more parameters onto a single model.
It's a fundamental shift. It's not about training one giant brain anymore. It's about training a brilliant and fiscally responsible manager for lots of smaller specialized brains.
And the paper even hints at what's next, suggesting we could develop more sophisticated recursive orchestrator systems.
So like orchestrators managing other orchestrators.
Exactly. Imagine multiple layers of these managers, each handling different tiers of tools. A hierarchy like that could potentially push the boundaries of intelligence and efficiency even further for really massive, complex tasks.
This research should definitely make you reconsider your own ML architecture planning. It's just a really strong data-backed argument for focusing on strategic resource management over just raw parameter count, especially when cost and user control are on the line.